Now, to find the potential for a polarized dielectric, we will put the dielectric material in the Cartesian coordinates. This is the polarized dielectric. It is already polarized, so it contains dipole, and let us assume it also contains a free charges, and we need at a certain point located at x, y, z, we need to calculate the potential, the electric field intensity, and the electric flux density at this point. So to do this, this polarized dielectric has a certain volume. Now we will select certain part from this material. We will take a differential volume dV dash from this material located at point x dash, y dash, and z dash, and we need to see the effect of this source on this field here. Now, due to these four types of charges, we will have the potential at point x, y, z will be due to the bond surface charge distribution and free surface charge distribution, bond volume charge distribution, free volume charge distribution. So we need to see the effect of these four charges individually on the point x, y, z. Now to start this equation, we will start with the equation of potential for a dipole, for one dipole. We take that V for one dipole equal P dot AR over 4 pi epsilon naught R square. This is the potential due to one dipole, but this material with this volume, the volume is bigger than one dipole, so if the material has more than one dipole, the polarization will be the summation of all the dipole moment. So this P is a dipole moment for one dipole. Now if we choose this dipole, we will talk about the differential potential because we are talking about one dipole. Now if the material contains more than one dipole, we need to consider the whole volume. In order to consider the whole volume, we need to integrate both sides with respect to the volume, and we will put here dash to represent the volume instead of the potential. So by integrating both sides, V equal P dot AR over 4 pi epsilon naught R square integration over V dash dV dash, while integrating both sides with respect to the volume. Okay, now let us assume that a gradient 1 over R equal, if we apply the gradient in spherical coordinate to a scalar equal 1 over R, it is equal to minus 1 over R square in AR direction. So gradient 1 over R equal minus AR over R square. So AR over R square, it is equal to minus gradient 1 over R, and AR over R square equal minus gradient 1 over R, and it is equal to del dash 1 over R. To get rid of the minus sign, we will choose del dash instead of del operator. The difference between del and del dash, the del means the derivative with respect to the field point xyz, while del dash, it is the derivative with respect to the x dash, y dash, z dash. Here in this problem, the problem is not in the field point because the field is fixed at a certain location. The problem it is in the source because the source has four different type of charges. So we need to focus on the source side of view. So we flip the coordinate system to focus on the source instead of the field point. So instead of AR over R square, we will put del dash 1 over R. So instead of this term here, AR over R square, we will put del 1 over R. So this equation will become V equal P dot del dash of 1 over R over 4 pi epsilon naught dV dash integration over V dash. So this integral we need to solve. Now, in order to solve this integral, we need a certain identity. Now this identity is divergence of VFA equal V equal to A dot gradient of V plus V multiplied by divergence of A. So we need to apply this identity on the previous integral, which is V equal P dot del dash 1 over R divided by 4 by epsilon naught dV dash integration over V dash. So by replacing V with 1 over R, A with P, del with del dash, we will see that this term here, P dot del dash 1 over R, is equivalent to A dot gradient of V. So this term here will be equal to this term minus this term. So we need to substitute these two terms inside this integral here and distribute the integral to the both terms. We will have the following relation: V equal divergence of P over R over 4 by epsilon naught dV dash integration over V dash minus V, which is 1 over R multiplied by divergence of P over 4 by epsilon naught dV dash integration over V dash. So we have two integral now, integral number 1 and integral number 2. Both integrals have divergence, but we need to apply divergence theorem only to integral number 1, since the integral number 1 has a difficult to solve derivative, while integral number 2, it is easy to find this derivative since it is function of P only. So by applying divergence theorem to integral number 1, the equation will become V equal P over R dot ds over 4 by epsilon naught integration around the closed surface plus minus divergence of P over 4 by epsilon naught R dV dash integration over V dash, and by replacing ds in the first integral by ds multiplied by A normal, since this is the definition of the normal surface area multiplied by the unit vector of the normal. So the equation now become V equal P dot A normal over 4 by epsilon naught R ds dash integration over S dash plus minus divergence of P divided by 4 by epsilon naught R dV dash integration over V dash. Now these two terms are used to find the potential due to the bond charges or polarized charges, while for free charges, now for free charges, if exist, we will calculate based on the equation previously described in chapter 4, V equal rho s ds over 4 by epsilon naught R using Coulomb's law integration over S for free surface charge distribution plus rho v dv over 4 by epsilon naught R integration over volume for free volume charge distribution if they exist. Now if we comparing this term with this term by duality, we will see that P dot A normal, it is equivalent to rho s. So P dot A normal, it is equivalent to rho s, but we need to replace rho s by rho ps, since this part here is responsible for the bonded charges. This part will be responsible for the bonded charges on the surface. since the integral is finding the potential for the charges on the surface, and the charge on the surface, it will be the positive charge, and the positive charge in the bonded charges, it will be called as bond surface charge distribution, while this term are calculating the potential due to the charges inside the volume, and the charges inside the volume in the bonded charge, which are the rho PV, which are the negative charges. So if we're comparing this part with this part, we will see that rho PS equal P dot A normal, and this equation is dual to this equation rho S equal D dot A normal found previously in chapter 4. And if we're comparing the second term for bonded charge with the second term of a free charge, we will notice that rho PV equal minus divergence of P, and this equation is dual to rho V equal divergence of D, which this equation we call it as first Maxwell's equation in integral form, and rho PV equal minus divergence of P. So the bonded charges will be calculated from the polarization vector, while the free charges will be calculated from the electric flux density vector. Now the negative sign here denoted that the charges remain within the volume are only the negative charges. So in order to calculate these charges, we need to find polarization in a way differ than the previous equation, which include the summation of all dipole moments, since physically it is not feasible to know the number of dipoles and the orientation of each dipole and the dipole moments inside any material, so it will be difficult to use that equation. So we need to find another simple equation to calculate the polarization.